Okay, part 3, here we go. So positive or negative acceleration, we're going to draw this. So moving in the positive position or positive direction and speeding up. All right, so it's going to be in the positive quadrant of the graph here. And since it's speeding up, that means it's covering more and more position in a shorter amount of time. So that is going to be a curve that looks like this. And let me make this a color for you. Make it thick. I'll make it this one. I'll make it purple. Okay. All right. Moving in the negative direction and speeding up. Okay, so that actually is going to look like this. No, don't move that. This is the one I want to move. So it starts off kind of slow, and then as time goes by, it gets faster and faster quickly in the negative direction. So getting farther and farther to that negative direction in a quicker amount of time. Moving in the positive direction and slowing down is going to look like this. So moving in the positive direction and slowing down is going to look like that. Yep, so that one's going to be that one. I was going to say, if this was a velocity time graph, we could also draw it coming back down towards 0. But since this is a position time graph, it's going to be in that direction. I guess, actually, hold on a second. So I had to think about it for a little bit, but actually you could draw this one like this also. This one is starting in the negative position, but it is moving in the positive direction. It's moving towards that positive, in the positive direction, and it's slowing down. So again, changing its position quickly at first, and then that position is changing less and less as time goes on. So moving in the negative direction and slowing down. Let me draw this for you real quick. Okay, so this one is going to look like this. I always have to think about these. This takes like some mental reasoning. Moving in the negative direction, so going down towards the negative direction and slowing down. And the reason I had to think about this is because this one can also look like this. Hold on. Let me get rid of that. This can also look like this. This is also moving in the negative direction, and it is also slowing down, okay? So it can be getting towards 0, or it can be getting farther and farther negative. Either way is fine. And I guess that said, this can also look like this, and this can also look like this. Okay? If this was a velocity time graph, we wouldn't be able to, we'd show it differently, but on a position time graph, that's what that's going to look like. Okay, describe the motion shown by the graph. In this graph, the object is speeding up in a positive direction away from the start. And in this graph, the object is slowing down in a positive direction. And if these graphs trip you up, like if you are able to show this in just the positive part of the graph, then you're good. Like you don't have to worry. I don't think there's going to be any negative stuff on the test except for maybe for MSA. But I just wanted to show you that. But like I said, if you can just see it on the positive part of the graph, you're in good shape. Okay, so let's come down here. So is the following explained by inertia or force equals mass times acceleration? So again, this is Newton's first law, this is Newton's second law. So if we have a small mass, then you get a large acceleration. Same force, but it blows this paper bag a lot, and it barely moves this car at all. So I am going to say that that is force equals mass times acceleration. And the reason why is, I mean, it's honestly, it's kind of both. You could really say it either way. You could say inertia. I mean, it all has to do with mass. inertia, the amount of inertia is determined by the amount of mass. So if this car is holding still, then it's going to take a lot more force to get it to move. Whereas this one has less because it has more inertia. This one has less inertia. But force equals mass times acceleration explains it because this is basically saying that. It's saying that the amount of force that you apply is, or the amount of net force, the amount that it actually, the amount of force that's moving it depends on the object's mass. If it's a more massive object, you're going to need a lot more force. If it's less massive, you're going to need less force. And the amount of acceleration that is already happening. So another way to say that would be like mass equals the net force divided by the acceleration. So either one really works, and it all has to do with the amount of mass there. More inertia for larger objects, less inertia for smaller objects, and it's all related based on this equation. I will have this answer for you when I post this. I'll write it down. So is the following phenomena explained by inertia or force equals mass times acceleration? This one is definitely inertia because as this car is slowing, because it's a much more massive object, then it's going to be slow. I guess you could explain this one both ways too. The car is going to slow at a slower rate than you. You, as a less massive object, are going to fly forward more. But both of them, the idea is that things that are moving want to keep moving at that same speed. So if there is something that's causing your car to stop, then anything that can keep moving in that car is going to keep moving. And that's why we wear seat belts. So let me get these two answers written for you. Okay, so I wanted to read you the final answers that I wrote here. So for this first one, you can explain it either way. Objects with more mass have more inertia, and they require more force to move and have less acceleration. So that's kind of both of those things wrapped up in one. Less mass leads to more acceleration with less force. So these two concepts are very much interrelated. And it all has to do with how much mass the object has, whether it's going to require more force or less. And this one, inertia is the easy, quick answer, right? Because that car is stopping, but you're going to keep moving until something causes you to stop. And what's going to cause you to stop is the unbalanced forces there. So Newton's second law is all about unbalanced forces, that you're going to keep moving at a constant rate until the unbalanced tension force of the seatbelt overcomes your forward motion. Okay? So thinking about net forces there. All right. Rank these objects from least to most acceleration. Okay, so we are going to change the letters and numbers in here to show what's going on here. So, okay, so this one is going to have no acceleration because all the forces are balanced. So I'm going to go ahead and say 1 for that one, least amount of acceleration there. This one is going to have 2 newtons of acceleration in that direction. So it could be slowing. It could have a forward motion here that we can't see, but there will be a force of acceleration there. So that's going to be 2. Okay, so now we have to do a little tiny bit of math. So I have 30 newtons in this direction and 15 newtons in this direction for a net force of 15 newtons. Compared to this one where I have 40 newtons and 10 newtons for a net force of 30 newtons. So this is going to be 3 right here. And this is going to be 4. So again, looking at what is the net force that's going on here. When we do the math about it, which force is going to overcome the other? So next one, what equation would you use to solve for net force? Okay, so we're just using this equation triangle right here. So if we're solving for net force, we're going to do F net equals mass times acceleration. And the answer is going to be in newtons because it's net force. So if we're solving for acceleration, then it's going to be A equals F net divided by acceleration. And again, divided by mass. And again, the way that I figure that out is I cover up whichever one I'm solving for. So here I was solving for acceleration, so I see that F net is over m, and the other way to think about that is that force has a direct relationship with acceleration, and mass has an inverse relationship with acceleration. F net divided by m. And if we're talking about acceleration, the units are going to be in meters per second squared. Insert special characters, soup, 2 meters per second squared. Okay, and if we're solving for mass, again, cover this up. F net divided by A. I'm just going to copy and paste it chunk by chunk. M equals F net divided by acceleration. And it's going to always be in kilograms. With other things that we've done, mass can be shown in pounds, it can be shown in milligrams, it can be shown in all kinds of different things. But when we're talking about forces, we do it with kilograms because newtons, if you'll remember, is actually a unit that wraps up all of those things. It's how much force it takes to move 1 kilogram of mass, accelerate it by 1 meter per second every second, okay? All right, so give the net force that is acting on the block and then calculate its acceleration. The net force that's acting on this block is going to be 26 newtons minus 12 newtons. 26 newtons minus 12 newtons equals, let's see, 24 newtons would be, it would leave us with 12. So this is going to be 14 newtons. See, there was 2 more here. And so if that is our net force, then the acceleration, oops, we need our thing here again. I'll just do it by memory though. F net divided by mass. Okay, so, oops. Come on now. Copy and then down here, paste. Okay, our F net is 14 newtons and our mass is 7 kilograms. So I can do this in my head. Our acceleration is going to be 2 meters per second squared. 2 meters per second squared. Okay. So here, my net force. This one I subtracted because they were going in opposite directions, so they were canceling each other out. But this one, they are adding to each other. So I have a total of 300 newtons plus 60 newtons here equals 360 newtons. And my acceleration then is going to be this one. So my F net is 360 newtons. And my mass is 40 kilograms. And, ooh, I should be able to do that in my head. I can feel that it's going to be like easy when I think about it. 360 divided by 40. 9. There you go. I knew it. So this is 9 meters per second squared. Okay. Next one. Use F net equals m times a to calculate the net force. So now we have the acceleration and we have the mass. We have these two. So we just need to calculate net force. So this is going to be pretty easy. I'm going to copy this and then make it much smaller. Okay, so the F net is, oh, that's what we're calculating for. So we have 9 kilograms and 3 meters per second squared. See you? Soup there. make this even smaller. Okay, so 9 times 3 is going to be 27 newtons.